Fast. So thanks everyone for joining. This is another seminar in our ongoing series of the IGS Global Seminar Series. So this week we have Dominik Fahrner, who is a postdoc at GEUS in Denmark, or sorry, maybe not a postdoc or a postdoc. Postdoc, there we go. A postdoc at GEUS in Denmark. Dominik recently moved to Denmark. He was a postdoc at Oregon and is now back in Europe. And he is presenting today on some work that he's done on tidewater glaciers around Greenland. And specifically, Dominik is presenting in this seminar series because he was the recipient of the Graeme Cogley Award last year. So in recognition of that, I'm going to pass it over to Hester, who is going to introduce and say a few words on the Graeme Cogley Award. And then we'll pass it over to Dominik for his presentation.
Yeah, thank you, Dave, and welcome, Dominic. So the Graeme Cogley Award is an award for early career researchers that have published a really good paper, either in the Journal of Glaciology or the Annals of Glaciology. And it was established after the unfortunate death of Graeme Cogley, who was a famous glaciologist and did a lot of things related to worldwide glacier monitoring and glacier mass balance change. But he was also the chief editor of the Journal of Glaciology until his death. And then the family actually wanted to do something, and this is how the Graeme Cogley Award was established. Now, the Graeme Cogley Award is actually shared between the IGS and IACS, and we award it in alternate years. So in the even years, the IGS will give out 2 Graeme Cogley Awards to students who've published papers of exceptional quality, either in the Journal of Glaciology or the Annals of Glaciology. So when you submit a paper to either the Journal of the Annals, you can indicate whether you are a student. And even if you've graduated like 3 months before that, you can still be eligible for this award. So we were a little bit delayed, but we're talking about the 2022 Graeme Cogley Award. So we actually had 123 student authored papers in the journal and the annals that we could choose from. Then the procedure, if you want to know the details, you can look on the link over here. But it's basically the IGS Associate Chief Editor. So there's 4 or 5 editors that look through all of them. That we shortlisted of these 123 papers. We shortlisted 13 papers of 6 countries, and the 2 winners were Dominik Fahrner, who at that time, or when he did his PhD, was at the University of Liverpool, and he published a paper on the linear response of the Greenland ice sheets tidewater terminus positions to climate. And the other winner was Mickey Mackay, who actually gave a talk earlier this year in the IGS seminar too. So what do the recipients of the Graeme Cogley Award get? Well, they get officially printed award certificates. They get award money, and this award money, 500 Canadian dollars, is sponsored by the Cogley family. So thank you to mostly the widow of Graeme Cogley, Kathy Cogley. They're actually recorded in the IGS official award recipient list, so they will be forever online in the annals there. And they present in an IGS Global Seminar Series. So Mickey actually gave her presentation on the 31st of January, and today we have Dominik. I just want to acknowledge that so there were 13 shortlisted papers with 2 winners. So there's 11 shortlisted candidates that also got a little bit of exposure. I sent an email to the cryo list to announce this too. So there's a whole diversity of papers, including on like snow avalanches, on glacier hazards, alpine glaciers, sea ice, of, as I said, 6 different countries in the world. So I just would like to briefly acknowledge these people with their excellent papers too. So now it's time, I think, for Dominik to actually explain a little bit what his work then was and what his current work is, perhaps.
Yes.
So congrats,
Thank you very
Dominic.
much. Thank you very much. I hope you can all see my screen. Great. Yes. Thank you very much for the introduction. I'm incredibly honored to have received this award for my work as a PhD student. And I will be presenting on what I've done during my PhD. So about the paper that I've won the award for, what I've done as a postdoc at the University of Oregon, and I'll briefly touch on what I've been doing these past 2 months at GEUS. So I will dive right in. We all know that glaciers are retreating in Greenland, and they've been thinning and accelerating since the mid-1990s. And I always like to show this graphic from NASA, which shows the mass loss from the Greenland ice sheet over the past 20 years or so. What you can see is there are certain regions where the Greenland ice sheet is losing more mass than in other regions. So if you can see my cursor here, in the west, for example, we have Jakobshavn Isbrae, which is a large outlet glacier of the Greenland ice sheet, and it's losing more mass than, for example, on the northeast coast. So what is quite obvious from this graphic here is that tidewater glaciers are the outlet of the Greenland ice sheet. And this has a global impact. So the Greenland ice sheet holds about 7 meters of global sea level rise. So we should all be concerned about what the tidewater glaciers are doing. What is also quite evident from this graphic here, if we look at July 2021, which is the last date of this graphic, is that there's a large spatial variability of where Greenland is losing mass. And I'll get to that a little bit later in my talk, why that is important. There are also some lesser known impacts that the retreat of tidewater glaciers has on a global scale as well as on a local scale. So it can affect large scale ocean currents, such as the Atlantic Meridional Overturning Current, through the influx of fresh water, through iceberg calving, for example, or just submarine melting or surface melting, any way that fresh water can enter the ocean, which then also impacts marine ecosystems. So the second picture that you see here is a large algae bloom off the coast of southwest Greenland. And that impacts primary and secondary production, which then in turn can also impact the economy in Greenland and the society. So there's been some large migration patterns of fish throughout the last century, and Greenland has invested of building plants to process this fish for export, which then had to be shut down because the fish were no longer there, which then in turn caused people to migrate to other parts of the country. We also associate some natural hazards with the retreat of glaciers. You can imagine if a large glacier retreats, the flanks of the valley where the glacier is retreating into is unstable, and it can cause landslides. And if they hit the water, they can cause tsunamis. So you can see there are many impacts of the retreat of tidewater glaciers. So the question is, what drives the retreat of tidewater glaciers? And that is unfortunately not a simple question to answer, because tidewater glaciers are inherently difficult to understand because they're influenced by a lot of different things. So they're influenced by bedrock topography, fjord geometry, subglacial hydrology, submarine melting, surface melting, iceberg calving, and climate forcings. So on the right is just a little graphic. The top bit shows subglacial hydrology. So you have a mix of channelized systems and branched out systems. You have plumes at the front of the glacier, moulins, crevasses, and then the bottom bit shows different ways of like ocean temperatures causing melting at the glacier terminus. So there's a lot going on. And the big problem is that of most of these influential drivers, we don't really know much about. For example, bedrock topography. still at most glaciers has large uncertainties associated with it. Subglacial hydrologies, there's very few observations of actually what's happening at the bed of a glacier. Submarine melting, it's very difficult to measure ocean temperatures or anything at the front of tidewater glaciers. Iceberg calving, we're still looking for a universal calving law, which is not trivial to solve. And then climate forcings. There's air temperatures, ocean temperatures. How do they interact with tidewater glaciers? We still don't really know. So my take on contributing to solving that question was to manually delineate tidewater glacier margins for most tidewater glaciers in Greenland using the Google Earth Engine digitization tool, or short GEDIT, which was developed by James Lee, my PhD supervisor. And it allows you to load satellite imagery into a cloud and then just manually draw a line where the glacier was at a certain time. So I used NASA Landsat 4 to 8 satellite imagery, and where we couldn't find a cloud-free image for a specific glacier, we used Sentinel-2 imagery. So on the right, you can see an example of the data set that we've created for Jakobshavn-Nisbrae. You can see tidewater margin delineations from 1985 to 2017. And obviously, this comes with some limitations. It depends on the resolution of the satellite imagery, how accurate you can be. So for Landsat 8, for example, the highest resolution you can get is 15 meters, whereas for Landsat 4, it's 30 meters. So you're always within like plus minus 30 to 15 meters. Then there's shadows and clouds that can obscure the terminus, so you don't get observations for every single image that you look at. And then, for example, you have the scanline corrective failure of Landsat 7, which produces images like this one, where you have like large gaps at the terminus, and then you have to decide if you either want to guess where the terminus is in that gap, or you don't delineate at all. And you have the human error, which is generally smaller than the pixel resolution of 15 meters. So for Landsat 8, it's about 3 meters, and for Landsat 4, it's about 6 meters. So you're within uncertainties here. So after 3 months delineating tidewater glacier margins for most glaciers in Greenland, I had a data set with observations for 206 tidewater glaciers. I had a total of 3,801 individual margin observations for the period 1984 to 2017. And you can see which glaciers we have observations for. And I published this data set as part of my paper, but it is now incorporated in the TermPix data set, which is a combination of all available margins. And we wanted to look at how climate influences the margin change over time. So we used regional climate data. So we used sea surface temperatures from the HADIS version 1 dataset, which we annually and regionally averaged. So you can see on the right-hand side, we created a buffer around the Greenland coast and selected all sea surface temperature data points within these buffers. We used air temperatures for some select weather stations from the Danish Meteorological Institute, which are indicated by these pink triangles here. And we used runoff from the Model Atmospheric Regional, or MAR. We also annually and regionally averaged those, and we took ice discharge from Ken Mankoff's discharge product, which we regionally averaged. We also looked at local climate data, so we didn't only look at the regional tidewater glacier retreat, but also individual, because we already had the data, so we thought we might as well look at things individually. So we again took sea surface temperatures from the HADIS version 1 dataset, but this time we used a KD tree analysis to identify the 4 closest points to the glacier, and only looked at those For air temperatures, this time took reanalysis data from the Danish Meteorological Institute's HIRAM-5 model, and we applied a 20-kilometer buffer for each glacier, so that we're not using weather stations that are like 500 kilometers away. And we chose to look at deep water ocean temperatures, which were taken from the World Ocean Atlas 2018. At the time, they only had decadal averages available, which is a pity because we wanted to look at annual values rather than decadal averages, but we thought it's good to include them anyway. And we again use a KD tree analysis to identify the 4 closest points, which gives you, as an example, a graphic like this. So you have the glacier where the star is, and then you have 4 sea surface temperature points, and then you have decadal averages for deep water ocean temperatures. Obviously, you can't just delineate margins and then infer something. So we quantified the change for every single tidewater glacier by using the margin change quantification tool, or MAKE-IT, which was also developed by James Lee. And we used the curvilinear box method to account for changes in fjord geometry. So the normal, or the more standard way of doing this is the centerline method, where you just look at 2 points and how they change over time, whereas we also take fjord geometry into account. So if we look at this example down here, so you have the glacier termini and then the box that is used to calculate the terminus change. For this specific example, the fjord is relatively straight, so it doesn't really matter if you use the centerline method or the curvilinear box method. But if you look at this fjord, which is for Narseb Sirmia in southwest Greenland, the fjord is more curved. So it actually does matter if you use the curvilinear box method, because you have more retreat in the center than you have at the edges. And as we cannot plot every single glacier on the same axis and then look at them combined, we had to normalize the margin change between 0 and 1 using min-max feature scaling, where 0 is the most retreated and 1 is the most advanced. We wanted to infer trends on a regional or Greenland ice sheet-wide scale. So we grouped the tidewater glaciers by region and then averaged them annually. And we determined the region just simply by using the ice divides. And what we found was quite surprising for us. So in the top panel here, you have the normalized annually averaged margin change over time for the southwest and the southeast. And then this panel over here is summer air temperature anomalies, and at the bottom you have sea surface temperature anomalies. And what is quite surprising to see is that we actually are quite spot on with when we see retreat starting, which is in the mid to late 1990s. But what is more surprising is that the retreat regionally is linear rather than individual tidewater glacier, which is more seasonally variable. And if you just put a straight line and look at the sea surface temperature anomalies and air temperature anomalies, you can see that it roughly coincides with an increase in both of them. And if we look at the same for the northwest and the northeast, we can see once again that retreat is starting in the late 1990s to early 2000s, which kind of makes sense when you think about the northward migration of warmer climate over time. And we again see linear retreat. In the northeast, you can see that we actually have continued retreat since 1984. And then we see an acceleration of retreat in the early 2000s. And again, it roughly occurs alongside increases in sea surface temperatures and summer air temperature anomalies. We didn't only want to like just identify these relationships visually, so we did a linear correlation, and what we found is a strong negative correlation between sea surface temperature and terminus behavior in the northwest, which you can see here in the yellow box, and between summer air temperatures and terminus behavior in the southeast region, which you can see in the bottom yellow box. So we did correlate all climate forcings that we were looking at, so runoff and other seasonal air temperature anomalies with all regions. And while we did find some other correlations, none of them were as strong as those two. So we figured that these must be dominant drivers of tidewater glacier margin advance and retreat in the respective region. But unfortunately, as it is with tidewater glaciers and climate, it's not that simple, because all climate variables are correlated to each other. So on the right-hand side, you can see a correlation matrix for all of the climate variables that we looked at and how they relate to each other. And every value here that is above 0.01, which is a p-value, is basically statistically not relevant, which makes it significantly more complicated to figure out what is actually the driver of tidewater glacier behavior. We therefore did a co-integration test, which is not commonly known in glaciology because it comes from economics, but it determines whether two time series are statistically relevant to each other. So there are two ways you can do that. One is the Engler-Granger test, which is checking if there is a statistically relevant connection between one independent and one dependent variable, and the Johansen test, which checks the same, just that you can have multiple independent and one dependent variable. And when we did the Engler-Granger test, we found that we actually were spot on with our linear correlation, because we only found a co-integration for sea surface temperatures and summer air temperature anomalies in the northwest. So this is indicated here in this table by having an H value of 1, and we have a slightly high p-value, but in this case the H value trumps the p-value. And then we did a Johansen test, and we did that rather than looking at regions. We did it for every single glacier and then averaged what we found. And we found that in the northwest, we again have the highest co-integration between sea surface temperatures and tidewater glacier behavior. And in the southeast, the same for summer air temperatures and tidewater glacier behavior. But what this figure also shows is that we have a lot of glaciers that actually are co-integrated with more than one climate variable, which suggests that there's a high variability, even with neighboring glaciers, of like how sensitive they are to different climate forcings. So this kind of shows that there might be some climate forcings that are more important than others, but it also at the same shows that most climate forcings are working in correspondence to each other. We also wanted to see if what ice discharge does when glaciers are retreating. So in our time frame and for the glaciers that we looked at, we found that 90% of the tidewater glaciers that we're looking at are retreating, and on a regional and Greenland ice sheet wide scale, discharge is increasing. However, we also found that almost 3/4 of the increase in discharge can be accounted for by just looking at 11 glaciers. So in the table, you can see that 11 glaciers contribute the most to ice discharge, even though many others are retreating, which means that tidewater glacier retreat does not equally mean an increase in discharge. As an example, you can see here the ice discharge for Southeast Greenland. On the left, that's all the tidewater glaciers that are included in our study. And on the right, it's the same, just without data for Helheim Glacier and Kangerlussuaq Glacier. What is quite surprising here is that we see a large spike in 2000 of about an increase of 40 gigatons a year in discharge. Whereas if we take out these two glaciers, while we do see some increases, if you would average it out over time, it would actually be relatively stable. And the same is true when you look at it for the Greenland ice sheet. So on the left, again, you have the whole Greenland ice sheet, and on the right in panel D, you have the Greenland ice sheet without these 11 fastest flowing tidewater glaciers. So it really is true that if we would take out these 11 fast flowing glaciers, ice discharge would remain relatively stable despite many glaciers retreating. And this brings me to my first sort of summary. So we did a qualitative analysis that shows that regional retreat is linear, with the caveat that we cannot use this relationship in projecting any tidewater glacier behavior into the future. We found that retreat is influenced in some regions by summer air temperatures. However, we assumed that the air temperatures that we take from one weather station is regionally uniform. And most importantly, we found that retreat is influenced by sea surface temperatures. However, we use sea surface temperatures as an indicator for deep water ocean temperatures. And many previous studies have shown that ocean temperatures had significant impact on the retreat of tidewater glaciers in the past. So for moving on from my PhD, my main question is can we quantify the influence of ocean forcing on tidewater glaciers? And if we can do that, can we use that to project what is going to happen to tidewater glaciers in the future should oceans warm more? So I was lucky enough to get a postdoc in the Greenland Ice Sheet Ocean Science Network, or GRISO. And I was part of the Ocean Forcing Ice Working Group, which consisted of all these amazing people. And it was an interdisciplinary group made up of ice sheet modelers, ice ocean researchers, and oceanographers, as well as glaciologists. And we came up with some goals for this working group, one of which was to estimate frontal ablation for 49 tidewater glaciers in Greenland using only open source observational data. And we wanted to get the best temporal resolution that we can get for the longest time frame that is possible. We used 49 tidewater glaciers because we also wanted to check if silts have an influence on what tidewater glacier behavior is doing and how it relates to ocean warming. So we selected those 49 glaciers based on the BET machine version 4 bathymetry, how reliable it is, and the results of Mike Wood's 2021 paper, where he identified that we actually have not good bathymetry for almost all glaciers in Greenland. We also wanted to establish a relationship between frontal ablation and ocean forcing in a more quantitative way and validate existing parameterizations that are currently used to run ice sheet models and see if they're still valid for the observational data that we produce. And if they do, great. And if they're not, we wanted to develop an improved parameterization of ocean forcing so that we can reduce the uncertainties in numerical models. And on the map on the right here, you can see just a combination of CTD measurements of ocean forcing And it looks like quite a lot, but it's actually not, and I will get to that in a little bit. So starting with estimating frontal ablation, how did we actually do that? So we tried to use only open source observational data. And we started with terminus positions from the Termpix dataset, which holds quite a lot of terminus positions for almost all tidewater glaciers in Greenland. We used surface elevation data. We used Arctic DM as well as Aerodem as two baselines for where the surface elevation was at a given time. We used surface elevation change measured by laser altimetry. We used bathymetry from Bed Machine, ice discharge from Ken Mankov's discharge product, and ice velocity to filter out some erroneous terminus positions. And from the table, you can see that they all have a very different spatial resolution, a different temporal coverage, and very different uncertainties. And as you can probably imagine, it wasn't quite trivial to bring them all together to get a temporally and spatially uniform data product. So I will explain a little bit more how we actually got a data set out of all these different input data sets. So we started out by delineating the fjord boundaries using a panchromatically sharpened NASA Landsat image. This is an example for a Helheim Glacier where you can see all the terminus positions that are available in the Termpix dataset, and then manually delineated fjord boundaries. So the orange is fjord boundary 1 and the bottom is fjord boundary 2. We then had to limit the terminus observations to 1 per month because we found that sometimes you have terminus observations that have been delineated on successive days, and there was quite a large discrepancy between them. So sometimes the glacier just cannot flow 3 kilometers in a day. So it was difficult to determine which of these observations is actually true. So we filtered them to 1 a month, usually whichever one is closest to the first of the month, to make sure that we don't get these large jumps in advance or retreat. And we then had to crop or extrapolate the terminus observation to the fjord boundaries. Sometimes the terminus delineation did not quite reach the fjord boundaries, which is when we extrapolated to the closest point on the fjord boundary. And if I go back one, you can see, for example, up here, some delineations actually go into the bedrock, and we had to clip these to the fjord boundaries. It was also quite difficult to actually determine where the certain endpoint is because people have drawn them from the top to the bottom or from the bottom to the top. So we also had to flip all these terminus positions into the right order. What we ended up with is something like this. So this is an example where we have a terminus position at time 1, which is the purple, and at time 2, which is the yellow. We have the fjord boundaries in red. And in this case, it indicates retreat over time. We then draw a reference boundary in the back upstream from the most retreated terminus position. And then we end up with polygons for each terminus observation. So A1 corresponds to time 1 and A2 corresponds to time 2. So we now have 2 areas, and we then want to know what is the actual mass loss at the terminus. So we need to calculate ice thickness for each of these terminus observation polygons. And we do that by using Arctic DM as a reference surface elevation, and then adjust for every terminus observation that we have. We lower the, or lower or higher the DEM based on the surface change rate if it's available. Otherwise, we just use a linear rate that we get from differencing the Arctic DM and the aerodem. And what we end up with is getting a nice thickness for every terminus observation polygon, which we then can use to calculate the volume and the mass. Obviously, we make some assumptions here. So we assume a uniform ice density with depth. We do not take crevasses into account. So we just assume this is a solid block of ice. We do not account for submarine melting in a way, because we assume a vertical terminus. So there's a lot of assumptions there, but with the lack of data that we're having, we actually cannot make any better guesses, basically. And what we then do is we determine terminus mass change between successive observations. So we basically just say volume 1 minus volume 2 is terminus change at time t1.5, which then allows us to calculate frontal ablation or estimate frontal ablation using the ice discharge product from Kamenkov. And we use the simple formula here, which is frontal ablation equals discharge minus terminus mass change. And we found out, unfortunately, that our monthly data has very large uncertainties associated with it, which is why we then used an averager to get 3 monthly observations, which significantly reduced our uncertainties, which then gave us these results. So the main result is here in panel A, where you have the terminus mass change over time in blue, the discharge from Kamenkov in green, and our frontal ablation data in orange. And what is quite obvious from the start is that our frontal ablation data follows the overall trend of the discharge data, but we have a lot more seasonal variability. Panel B, you have the glacier velocity over time, and in panel C, you have terminus retreat or terminus position relative to the most recent observation. And this is just a map showing the terminus positions that we use to calculate our frontal ablation estimate. And this is quite important if you want to look at climate influence on tidewater glacier behavior, because from the discharge data, it's very smooth. Even though you have monthly observations, it is very smooth, and you lose this variability that is actually there because normal discharge products do not take terminus change into account. So if we look at all the glaciers that we investigated in this study, we found that the most dynamic tidewater glaciers contribute the most to total frontal ablation, which is over 15 gigatons a year. So here on this map, you can see that Jakobshavn is contributing about 42 gigatons a year to frontal ablation or to total mass loss. And then you have Kangerlussuaq and Helheim on the south coast, on the east coast, sorry, that also contribute quite a lot. But then you also have 7 other glaciers that, while they do not contribute as much, they still contribute a significant amount to the total mass loss of the Greenland ice sheet, with some of them listed here, which highlights that not only the most dynamic glaciers are responsible for the mass loss of the Greenland ice sheet. And I know we investigate, or we put an increased effort in figuring out what's going on at these glaciers, but we should not forget about the others. And one important aspect is that current ice discharge estimates do not include terminus position change. As I said before, that seriously limits our like how we can investigate the influence of climate forcing on glacier behavior. If we lose the seasonal variability, we basically ignore a crucial aspect of what the glacier is doing. And we've currently validated this data product against decadal estimates from Will Kochtitsky, and over 50% of our values are within 0.2 gigatons a year of their estimates, and over 80% are within 2 gigatons a year. Obviously, because we have a higher temporal resolution, it's a bit difficult to compare it to decadal values, and we're currently working on comparing it to Chad Green's recent data set that came out this year in Nature, where he's looking at mass loss for all glaciers of the Greenland ice sheet. But that is unfortunately still a work in progress. We then started to look at ocean data, and with ocean data, it's unfortunately still a bit difficult because there's still a lack of ocean data, especially on longer timescales. So we've compiled all the publicly available CTD data that we could find from the World Ocean Atlas for the International Consortium of Exploration of the Seas, Ocean Smelting Greenland. We also used the marine mammal database, and what we got, so this is an example for Helheim Glacier in the southeast, is a very limited time series. This might look like a lot of CTD casts, but unfortunately, it's still not enough data to derive a meaningful time series, which we then could use to compare to our frontal ablation estimates. So this necessitates the use of reanalysis data products. For example, Donald Slater averaged 4 reanalysis data products for ISMIP6, and we've been looking into using that. But unfortunately, there are still some issues. While these reanalysis data products are informed by observations, there's still a discrepancy because they've been using data that is outside of the fjord on the shelf and not directly at the terminus, which is what we were trying to do, to use the closest CTD measurement to the terminus. And when you use the data on the shelf, obviously there's still a lot of processes that go on within a fjord that could change the temperature of the ocean. Which leads me to the next steps and my current work. So we're still working on validating our frontal ablation data set against the monthly mass loss estimates from Chad Green. We would like to determine a sort of correction factor between the observational CTD data that we already have and the reanalysis ocean data. That would allow us to basically correct for the difference between taking ocean data from the shelf and projecting it right to the glacier terminus. And once we've done that, we can hopefully have a long-standing time series for every glacier in our current frontal ablation data set so that we can derive a relationship between frontal ablation and ocean forcing. We would also like to look at the influence of discharge on submarine melting. So does it actually make a difference for all glaciers if subglacial discharge is present? And does that enhance submarine melting at all glaciers? And I'm doing this currently at GEUS, and I'm part there of the Center of Ice Sheet and Sea Level Predictions. And I'll be investigating submarine melting at so-called end-member glaciers, one of which is Petermann, and the other one is Kangerlussuaq Glacier. Petermann because it has a large ice shelf, and Kangerlussuaq because it's actually not calving these big tabular icebergs, but rather smaller icebergs. And our plan is to use observational data to actually look at these two glaciers in particular and in detail. So in 2024, this summer, we will install 10 GPS stations across the grounding zone and upstream, as well as on the floating tongue of Petermann. And we'll install some automatic weather stations, which will hopefully give us some insights into what is happening, not only with on a glacier dynamic level, but also on a climate level for Petermann next year. And I'm going to sum up everything that I've said so far. So what I've done over the past couple of years is we've identified a regional trend of tidewater glacier retreat in all sectors of the Greenland ice sheet over the last decades. We found that summer air temperatures, as well as ocean forcing, appear to be most influential on tidewater glacier retreat. However, we can still not actually say if there's one single driver that drives tidewater glacier retreat, so we still cannot single out a single thing. There's not enough observational data to definitively determine what drives tidewater glacier retreat. So while we are increasing our efforts to get more data, it's still not enough. And in my opinion, the increased efforts should be focused on combining available ocean data. So there's still a lot of ocean data that has not been published or that is in some paper or in some repository. And it would really help if we could get them all into a single database that is quality controlled, which would then allow us to circumvent reanalysis data, at least for some glaciers, maybe not for all. And we could investigate submarine melting and the role of the ocean in tidewater glacier retreat. And that was all I had to say for today. Thank you very much for your attention. The terminus position data that I've presented here is available on Zenodo. And if anyone would like to use the frontal ablation estimate dataset or the processing chain, which will be published soon, hopefully, please just send me an email. The processing chain can be applied to any glacier in the world, depending on your input data. So you need to have a certain set of input data available. But in theory, you could calculate frontal ablation estimates for any glacier in the world. Thank you.
Excellent. Thank you, Dominic. That was a great talk. Very, very thorough. I'm just writing down a note. If anyone has any questions, please raise your hand or turn on your video and unmute yourself, and you can go ahead. Yes, Roland.
Hi. Fantastic talk, Dominic, and an incredible amount of work. I was wondering if you could give me a little bit more perspective. You mentioned these 11 glaciers that dominated the change in frontal ablation, I believe. Can you give me some perspective? Are they also a large proportion of the total ice discharge from Greenland in terms of its mass budget?
So I've mentioned two separate things. So there are 11 glaciers that have a very high ice discharge. And I've mentioned 6 glaciers that also contribute quite a lot to mass loss. So I think for both, well, let's start a different way. So the 6 glaciers that also contribute significantly to the mass loss of the Greenland ice sheet also have a relatively high discharge. The 11 glaciers that have a high discharge, they all retreated as well. So I don't know if that answered your questions, but let me see if I can just go back to that. So there's this graph here. So these are the 11 glaciers. So most of them showed an increase in discharge over the investigated time frame. So they did lose mass, but not, well, they did lose mass at an increased rate. Yeah. Did that answer your question? I'm happy to explain it a bit more if I need
I'm
to.
still a little confused in that obviously if a terminus retreats, then that's, in this terminology, that's mass loss.
Yeah.
And what I'm seeing is were these big changes just seen because these are the big glaciers in terms of their total transport of ice out of Greenland? I'm used to working in an Antarctic context where one worries a lot more about the flux across the grounding line in terms of, where are you putting volume into the ocean rather than the separate issue of where an ice shelf front might be. And so I was just trying to get clear whether, I guess my question is, are there some very significant outlet glaciers in Greenland that don't show these changes in frontal ablation?
Yeah. I mean, there are definitely some glaciers that are relatively stable, where ice discharge is stable, frontal ablation is stable, and they don't do very much. In this case here, these are all retreating. They all have a relatively high discharge, so they have a relatively high mass loss.
Thank you.
Okay.
Yes, Francisco.
Hello, really nice talk. It was just a pity that many people could not maybe attend just because of this confusion about the timing. Anyway, you have mentioned the rather good agreement with the estimates, the decadal estimates by Will Kolchitsky. And you have also mentioned the recent paper by Green and others in Nature. But do you know whether, how is the kind of agreement between Green and Kolchitsky? Because I was surprised that in this Green paper, it was not mentioned at all, even as a reference, the work by Kolchitsky. I mean, I didn't have an opportunity to look at it in detail, and maybe you are more familiar with that, or you have some feeling, or maybe just telling what is the kind of agreement of your own work with that of Green, then that would provide a cue about the other question.
Yeah. So, yeah, I mean, I haven't looked into how Kochtitsky and Green agree because it's very different data product. So Will's work is decadal, so they have like values for every decade, whereas Jack Green's work is monthly data from 1972 to 2020. And Will was actually looking at frontal ablation, whereas like I've spent quite a lot of time with Jack Green's data, and it's more mass loss rather than frontal ablation. So they looked at catchment-wide mass loss, whereas Will looked at like glacier scale. If we use the same, I think the big difference between what I've been doing and what Jack Green's been doing is we use different ice thicknesses, and that makes a big difference. So we calculate ice thickness for every time step that we look at, whereas Jack Green is using an inversion algorithm for bed machine and doesn't adjust for changes in time. So if I use the same ice thicknesses that I use for my data product with Chad Green's area change, we actually are in almost perfect agreement with the numbers. But if I would use his, I've been actually working on that today, so I don't have an answer for you on that.
Okay, thank you.
Yeah, no problem.
So I have a question that's kind of related that maybe links everything because it's about uncertainty. So you are now working on submarine ablation, which actually may be well within the uncertainty of, surface mass balance or the frontal mass balance relationship. So, you're fine-tuning certain things that you can, but maybe in the bigger scale, it doesn't really make that much of a difference. So how do you make that decision of what you're going to work on next based on those uncertainties? Because I think part of the issue with flux data is also like where the flux gate is. So like with in our paper, the Koptitsky, we have it in a certain location, and we know that if you do it a little bit upstream or downstream, you have a difference. So
yeah, that is very true. So we actually looked at the discharge from Will and ours, and for Jakobshavn, we have a big discrepancy of about 10 gigatons a year. That is just because our Kamenko's flux gate is in a different location. So obviously, when you then calculate frontal ablation, you get very different values. So yeah, we do the best we can with the data that we have. What we wanted to do mainly with this project was to also provide a processing chain that is easy to use, can use any data that you throw at it, and that is publicly available. In terms of submarine melting and uncertainty, it's still a big issue in numerical ice sheet models. And when we project sea level rise, submarine melting, while we do have some parameterizations for that, it's still not really well constrained. So that was one of the reasons why I started doing this work, to actually help to better constrain it with using observational data. Unfortunately, I did not get to the point that I wanted to be at in 2 years, because everything takes so much longer when you have so much data to work with.
Interesting. That brings us to the top of the hour. Any other questions? Any other comments? No. All right.
One
Well,
quick question. Yeah, you mentioned this issue of submarine melting, and you also mentioned that you'll be going to Petermann. Is there comprehensive data that would define a grounding line or a tidal hinge zone or something for these glaciers? Is there something identifiable upstream of the calving front in most of these situations? Just thinking of these massive compilations that get done for Antarctica with lots of INSAR calculations of a grounding zone.
For Petermann, we have a pretty good idea where the grounding zone is from INSAR data. But it's one of the only floating glaciers with a floating tongue, where you can then actually look at tidal hinges and stuff like that. I think for most of the other glaciers, we know where the grounding zone is, but the tidal effect is negligible. But yeah, such a database of where is the grounding zone does exist. The bigger problem with submarine melting is we have no ocean data at the terminus, where we just don't know. Is it the same as on the shelf? Can we infer that it just goes in? Is it undercutting? How much is it undercutting? There's a couple of papers where they actually did multi-beam sonar at a glacier terminus, where they imaged the glacier front, and they could actually see undercutting of up to 200 meters wide. So that would be something that would be really cool to do at all glaciers in Greenland, but obviously that is a big financial problem.
And a big risk to losing your UAV potentially under the ice tongue.
Yeah.
Oh. Sorry about that. Anyways, yeah, that brings us to a close. So thanks very much, Dominic, and thanks to everyone for I think a great discussion this week. I think there's a lot of really, really good questions there. So thanks again, Dominic. Congratulations on the award, and thank you for giving such a great talk. Before we go, I will plug that next week we have Dr. Melinda Webster from the University of Washington, who's going to be presenting on snow on sea ice. And that will be at the normal time, which is 9 p.m. London time, which I will make sure to clarify with the other chairs and to also make sure that that's included in the CryoList ad that goes out next week. So thanks everyone for making it. Those of you in Europe, thanks for staying up late. And I hope you all have a good rest of the week.
Okay. Thank you. Bye.
Thanks,
Bye.
Dominic. Great talk.
Thanks. Bye.